And that's why today we're going to talk about data visualization in Python using Matplotlib. Just to start, as we always do, let's give you a schedule of what we're going to cover today. We're going to start with what is data visualization? What does it actually mean? What is Matplotlib? Let's talk about some components of a graph. We're going to talk about how we visualize different types of data, and then we're going to get into the principles of data visualization. And I do want to mention today we are using an external resource besides what I've already included for the course. Today we're going to use a digital ebook that comes from a Harvard professor, which talks about an introduction to data science. So if you want a little bit more background, check out that link. Now let's just start with what can we do? What kind of plots can we make? And really, there are hundreds of different ways to display data, but here are some of our common ones. We can use scatter plots, we can use histograms, we can use violin plots, we can use contour maps, we can use box plots, we can use bar graphs. So there's tons and tons of ways to look at the same type of data and different type of data. And as we need new types of graphs, I'm sure new types of graphs will be invented. And I do specifically want to point out that I did not make this visualization. This is great, a great summary of Matplotlib. This comes from Rizky, and he wrote 2 Medium articles about how we can use Matplotlib. So what is data visualization? The fact of the matter is, staring at tables with numbers and words that represent categories is not helpful for almost anyone in the world. And we know this to be true because we have a saying that is, a picture is worth 1,000 words. And that is factually accurate. The majority of people are visual learners, over 50%, and I think the statistic is closer to 65 or 70% of people learn better visually. They want to see something and be able to gather information from it. Okay, so there is so much data available in the world, and every part of our world relies on it now. Anything from academia all the way down to industry is reliant on data and data analysis. And we've talked about this before. When we were in our first couple weeks of class, we talked about the fact that basically each year it feels like there's a new data analyst type position that starts opening up. This year it was business analyst became a really big thing. And that's because everybody's got a problem that they want to solve, and they need somebody to run the data, create visualizations, and extract information from it. So a perfect example of all three of these worlds colliding would be something like the news or the media during the COVID pandemic. Wall Street, for instance, was posting, I think, probably daily updates on the COVID pandemic, and all of those included a graph of where the infection rates were at and who or where we thought they were coming in from. And so all of that takes data analysis, and then once they analyze the data, they create visualizations, which then get published. So that's kind of an intersection of all three of these worlds: academia, government, and industry. Academia, because that's where the data analysts or data scientists likely learn their skills. Government, because they're the ones providing the numbers. And then industry, because Wall Street is posting those kind of articles. Excuse me, not Wall Street. Wall Street Journal or New York Press or whoever it is was posting the articles with the data visualizations in it. So we're going to keep our definition of data visualization simple. Okay, basically data visualization for us is a visual communication of results from data. So if we had this piece of information here, we gathered some data, okay, we're going to extract it, analyze it, find out what it's telling us, and then we're going to turn it into a picture. So for us, that's what data visualization is: creating a visual communication of your results from your data. Okay? Now, we're going to do this through a software package called Matplotlib. And Matplotlib is built on top of NumPy, so it's perfect for working with arrays and working with pandas and our data science background that we've already developed. And then it's also designed for application with SciPy. And we might get into SciPy earlier. I'm not sure how deep we'll go, or not earlier, later. And if we don't go all the way into SciPy, we'll definitely go into scikit-learn, which is a base module of SciPy. And Matplotlib is extremely robust. It works on all major operating systems and has a very robust graphics backend. And the part of the reason for this is they took what they're calling an everything to everyone approach. So no matter where you are in the world, no matter what system you have or whatever limitations you may have, Matplotlib will make a graph for you on that computer that you have access to. Okay, so that was really the goal with this package. And this package has been around for a very long time. I think we're approaching 20 years of use, and it's very easy to learn. There's really no need to memorize functions. I would say that as you practice with it, you will pick up on patterns or like keywords that are important, of course. But most of the time, honestly, people just Google. You can sit there and Google Matplotlib cheat sheet or Matplotlib style sheet, and you'll find an exact reference for how you should make your plot for the data that you were analyzing. And like I said, Matplotlib is starting age a little bit, but it's still extremely useful. It still gets updated. It's not deprecated. Some people would argue that R, the statistical programming language, has newer, slightly more robust graphics capabilities. I really don't think it's that different. I would say that R's graphing capabilities may be slightly faster computationally, or maybe more efficient computationally is what I'll say. And that's because they have a newer program called ggplot, which is extremely useful, and we can map ggplot to matplotlib. The functions are very, very similar. Now, as far as what is actually going to be in our graphs, we have three main components or three main categories. Well, first off, the data, right? You've got to have data to have something to graph. So what are we studying? What problem are we trying to solve? And as always, it's important to understand the situation that you're trying to help, right? The geometry. The geometry basically describes the type of plot that you're using to display your data. Okay, so whether it's a scatter plot or a histogram or a box plot or a bar graph, a contour plot, three-dimensional box plot, I don't know, whatever it may be. The geometry is what describes how that graph is laid out. And then the aesthetics. The aesthetics are just the representation of the detail found in your data. So this would be things like categories on your X and Y axis, your title, your legend, how the data is grouped. Should the graphs be side by side with each other? Do we want to use different colors? Those are all the aesthetic features of our graphs. Now, with these graphs, obviously we have to have data, as I said, to make a graph. So there's a bunch of different types of data, and we're going to talk about some of the different distributions. Okay, so this starts to get a little bit more into the specific statistics. So there are many different distributions of data, and there's basically two ways that we need to break it up. Okay, first off is continuous versus discrete, and then qualitative versus quantitative data. So continuous versus discrete. Discrete data is things like whole numbers or concrete fixed values. So when we're talking about whole numbers, I mean 1, 2, 3, 4, 5, 6, no decimals, no floats, or concrete values like it's either yes or no, like a Boolean, or it has to fit a category like red, green, blue, purple. Okay, whereas continuous data is an data that has an infinite number of possibilities. So like if we're measuring people's heights, for instance, I could be 5 foot, I could be 5'1", I could be 5'1" and a quarter, I could be 5'1" and 6/18, I could be 5'1" and 9/32, whatever it is, right? It is a never-ending measurement. So there could be any number of possible in between values between the whole numbers on that graph or on that diagram or that measurement. Okay, it's an infinite number of possibilities, technically speaking. And then let's separate qualitative versus quantitative data. So qualitative data is data that fits into categories or groups. So when we're talking about yes, no, red, green, blue, purple, those would be examples of qualitative data. These are things that commonly would be found on a survey. And with qualitative data, your options for representing them as charts or graphs is a little bit more limited. But also the data that you're gathering is slightly more limited, right? You have a more limited number of possibilities that you are grabbing. So these are typically represented with bar charts. You also could represent them with something like a pie chart. If you wanted to do proportions or percentages, but really you don't have that much variety when it comes to qualitative data. Now with quantitative data, you expect your data to be a numerical measurement, as in I defined a value like the height of the grass outside, and I went and measured the height of the grass in 16 different areas, and then I took in weather data, and we just have an infinite number of possibilities here, so we're expecting more complexity. And with quantitative data, we do have options, or more options, like histograms, box plots, scatter plots. A phylogenetic tree could be a representation of a quantitative data set, like you saw on the very first screen, the title slide. And if we look over here on our right, I've got two different examples for you. So on the top here would be an example of qualitative data. This graph is showing us the proportion of population based on region in an area: northeast, south, north, central, west. And so we are just measuring based on those categories. We're measuring the number of people that live there, right? So that's a whole number, discrete value, and we're representing that as a proportion on a bar chart. Whereas the bottom one here is quantitative data, excuse me. So we are measuring the continents and the population size on those continents as a box plot, which shows us the mean, median, mode, interquartile range, highs and lows. Okay, so there's more data displayed there because there is technically an infinite number of possibilities, a wider range. So now let's dive into some of our principles of data visualization. And of course, you'll get practice with these as we go through some of our assignments and guided projects. But for right now, we're gonna narrow it down to 7 things, and I don't expect you to have these memorized. I'm just providing them to you at this time. So number 1, know when to include 0. This may sound silly because I bet 99% of the time that you've ever drawn a graph or made a graph for a class, you've always included 0 at the base of your y-axis. But in some instances, including 0 can actually hurt how your data is represented. So over here on this left-hand graph, this is a perfect example. On the x-axis, we are looking at the continent, so the continent is basically the way that we're grouping things, and we're measuring the life expectancy on the y-axis here to tell us which continents have people that live the longest. Well, if we look at our graph here, based on our range, or our y-axis range, and how our data is grouped, you see that all of our data kind of falls into a cluster here, and all of the dots are sitting on top of each other. So we're not really gaining much information by looking at this graph. And that's the exact opposite of what we want a graph to do. We want a graph to provide us with more knowledge. Okay, so on the right here, we are going to know when to include 0, and we're going to recognize that including 0 in this situation is hurting our visualization of our data. So on the right graph here, we take the same data and we change the minimum value for our y-axis from 0 to 45. And the reason for that is 45 is the low end of the life expectancy for our data set. And you see what this allows us to do is really spread out the data here on the right side and start to see some differences between the continents here. So we see that Africa, for instance, has a wider range, more variability in life expectancy in comparison to America, Asia, Europe, Oceania. Okay, so this is why it's important to know when to include 0. It helps you sometimes removing 0 and representing your data in a better fashion. Number 2, do not distort your quantities. And this is exactly what it says. Don't misrepresent your data. That's basically what we're getting at here. And we are going to use good old President Barack Obama from his 2011 State of the Union address as our example here. So during this speech in 2011, Mr. Obama decided to discuss the American economy, as he should, and he specifically was discussing the gross domestic product. Okay, so this is the total, this is a total aggregation variable. Basically, it's the sum of everything you manufacture and ship out and process. And so it's a way that we represent the total size of our economy. And you'll see over here on this representation, they show that America, United States, has a total GDP of $14.6 trillion. And the next closest economy is China at a GDP of $5.7 trillion. So if we do some quick maths, we're going to round up and we're going to say that America is 15, China is $6 trillion. 15 divided by 6, and there's a little bit of leftovers there. We'll cross out the 6, make it a 5, and we can say that China essentially, in a very rough math here, China has an economy 3 times smaller than the US. Okay, now if we compare the size of the bubbles shown here for the United States versus China, you can pretty obviously see that the bubble showing the United States at the top there is much larger than 3 times the size of China, than China's bubble. You probably could fit China inside of the US there maybe 5 or 6 times in total. And so if we dive into the data a little bit closer, what you are seeing in this graphic that was used on national television to represent the size of our economy to the American people, what we are seeing is actually a representation of the American economy from the perspective of GDP. That's what we're measuring. The GDP of our economy based on the radius. So that $15 trillion is represented as the radius of that circle. And that's how they got that to be so big. Okay, so that they've altered, in actuality, they've altered the representation of the data to inflate it and make our economy look bigger than it is in comparison to our neighbors. Okay, if they would have accurately represented the data, it would have shown up like it is over here on the right side in this square. All right, and you can still clearly see that there is a difference between the US and China here, right? So if they had accurately represented the total size of our economy, they would have used the area of a circle to represent this data. That would have been the appropriate way to show, to quantify in this type of graph, the size of our economy. Okay, and they blatantly misrepresented the data to portray and show rhetoric to the American people. So that is why one of our principles is to not distort the quantity of your data. Accurately represent your data, and just remember that all data has value. It is not always going to be as impactful as you want, but it is still providing you with information which is useful if you are trying to answer a question. All right, off that rant. Number 3, order your categories meaningfully. This one is, I guess, up to personal preference in some ways. But the fact of the matter is, again, you're making this for somebody to look at. And so you want your graph to be intuitive, and you want somebody to be able to, as soon as they see it, to draw the conclusion that you're showing them with that graph, with that figure. And so our example here on the right is the murder rates across the US. And this graph on the left shows the murder rate based on state or district found across the US. Actually, both graphs do. But the one on the left-hand side that the arrow is pointing at has our states ordered alphabetically from A to Z. And what you'll notice, we can't really see a picture here. If we trace the curve of the data set here, we have multiple peaks. We have what looks like a high amount of variability. And this is where ordering the data comes into mind, because in Python or R, whatever graphing program you're using, they're likely going to default to ordering the data alphabetically, A, B, C, D, E. Okay, but in some instances, it makes sense to order based on high to low, or based on the average value, or however you feel the need to represent your data. So in this instance, when we're talking about murder rate, in my mind, personally, a high murder rate is a bad thing. Okay, so in our instance, let's regroup this data, recategorize this data from high to low to see if we can see any more trends. And that's what this graph is here on the right. And when we recategorize and reorder the data from highest to lowest murder rate, we very clearly have a trend in our data. Okay, so we start at this really high value in District of Columbia, we level off, and then it keeps getting lower. Okay, and if we dug into this even further, there are other socioeconomic factors that are obviously playing into this murder rate. But the fact of the matter is, in this instance, order did matter. In the first instance on the left here, we can't really pick out many conclusions there. We see 3 peaks, basically. When we reorder the data here on the right, we very clearly have different sections. We have outliers, we have our mean or our standard our standard murder rate, which is a sad thing to say, but a clear middle group, and then we have our low end outliers, which are probably based on population. So order of the data does impact how the data is seen by the end user. Number 4, show the data. Okay, so in our first example, let's go back to that. In our first example, we had, this one works fine. In our first example here, we had data that was too clumped together. Okay, and by deleting the 0 off of the y-axis, we allowed it to spread out and still be seen. Well, in the example we're currently on, we can do that again, all right? And in this case, we're comparing male versus female height. We can do that again. We can delete our 0 here, and we get a little bit of spread on the data. But what we're noticing is we still have these big regions of clumping where we can't really pull any information out. There's nothing to be gleaned from that era. So in this instance, this visualization isn't telling us much about the difference in height between males and females. So we can change the way this data is shown by just providing some space between the data points and zooming in. Okay, so this is the exact same representation of the male and the female data sets as what's above, but instead they're allowed to stack, and they're allowed to show all of the boxes and all of the bullet points instead of them being lined up on top of each other. So you just take this and spread it out. And that's a really easy fix to do. It'd be one line of code, but instead of having this black line that doesn't tell you anything, now you have your individual people on your chart, and you can see differences in color, differences in area of saturation. So showing your data is always going to benefit you when you're trying to get a point across to your audience. But the fact of the matter is, even if we show the data, in all instances, not in all instances is that the best way to show the data. Okay, and I know that sounds silly or it sounds counterintuitive, but sometimes there's an extra step you can take to really make it easy for someone to see what you are trying to show them. Okay, because again, when you're doing these analyses, you are trying to solve a problem. Okay, so this is the exact same data that we just saw before, and it's much cleaner. So in this instance, what we did is instead of having our plot with the sex on the bottom, the male and female, and then the height on our y-axis, and just showing some dots on the graph, what we did is we basically turned that graph sideways, and we made a female graph on the top and a male graph on the bottom. And instead of being scatter plots, or dot plots, whatever you want to call them, we turned them into histograms. So now we've split up the sexes into 2 different graphs, and we've moved the height onto the bottom axis, or onto the x-axis, excuse me. And then the y-axis is now density, which is like basically a measurement of frequency or proportion based on each possible answer, so based on the height in this instance. And this graph shows us so much more information about our data than even the scatter plot with the points spread out did, because here it's very, very clear where the majority of the female population sits as far as height goes, and where the majority of the male population sits as far as height goes. And what we can do is make comparisons between female and male here based on height, and we can see that there's a lot of overlap and just a little bit of difference. Males just tend to be slightly taller than females do on average, and that is statistically accurate. I believe the average height for like American females is 5'6", and the average height for American males is like 5'8" or 5'9". So there's just a slight difference in height between males and females. Now, in the same realm of things, sometimes there isn't a good way to draw conclusions from your data in its current forms. And to try to find an answer so that you didn't waste your time, or you don't have to go back to the drawing board, to try to find an answer, you can consider making transformations to your data. And in fact, in many cases, like especially if you're studying the environment where there's so much variability, you have to transform the data to be able to analyze it, or you will never find any differences, because there's just so much noise that you really can't get any statistical difference out of it. So Our example here is again looking at the population based on the continent that people are on. So continent is our x-axis, population in millions is our y-axis. And the original data set would be what we see here on the bottom. Okay, so we've got our continent again on our x-axis, population on the y-axis, and all we see is a bunch of clump dots towards the x-axis. We have very little information that can be gathered from this data at this point. We see a couple of dots that are off on their own towards the top that we can tell, and then we have two extreme outliers on the top, and these extreme outliers are the reason that we're having this problem with our data visualization. These two dots at the top here represent China and India. China, I believe, has a population of 1.5 billion and India is like 1.3 or something, and no one else in the world is even close. America would probably be the next highest population size, and we're 330 to 350 million people. So almost five times more the number of people in China than the US. Okay, so that's a major outlier, and it really skews the way the data is shown. We can fix this by transforming the data. So by log transforming the data, we can take the log of it and spread this data out, and that allows us to change our axis from a zero to 1.5 billion based axis to a log based axis on our y-axis. So we have 1, 10, 100, 1,000, which would be a billion people, and it really spreads out the data here. So now we can see our entire box plots. We can see all of the individual dots, all of the individual measurements on our box plot. It shows us our interquartile range, our mean, median, mode, all of the above. Okay, so sometimes you have to transform your data, and it really probably depends based on your discipline if you need to do that as a standard or not. And that's really, I would say that's really up to contention, or out for contention, whatever the phrasing is, in the academic world. Some people love transforming data. They think it provides some consistency. Other people hate it, and they would tell you not to ever transform your data. So I guess it just depends on what you prefer. And then lastly, as always, know your audience. We always talk about situational awareness, and it does not change with data visualization either. You have to know who your primary audience is. You have to know what problem you're solving and who it's going to impact, or who you're telling your story to. If you do not know, you're wasting your time. You will never have an impact. Your data visualization doesn't mean anything. It's not going to be intuitive. So you have to know who your audience is. And as Star Wars would tell us, these aren't the droids you're looking for. Well, in actuality, if you don't know your audience, those are the droids you're looking for, and you will be fired. So you have to know your audience to be able to properly visualize your data, just like you have to have your situational awareness when you're cleaning your data, just like you have to know what problems you are trying to solve with your data. Okay, it all builds on top of each other, and you've got to have a consistent story. So with that, that's all I had for you guys today. Thank you so much for being here. Thanks for taking the time to watch this video, and I will see you on Wednesday for our guided project. See you later.